RNA-loaded nanocapsules for the treatment of neurodegenerative diseases. This is a work carried out for BSmart project, funded by the European Commission. Neurodegenerative diseases such as Alzheimer's affect over 7 million people all over Europe. Despite this fact, few treatments for this group of diseases are available so far. Alzheimer's disease is characterized by the presence of beta-amyloid plaques and neurofibrillary tangles consisting of tau. Beta-secretase 1 or base-1 protein is considered a primary target for anti-amyloid therapeutic drug design, since downregulation of base results in lowering beta-amyloid secretion. The objective of BSmart project is to develop an RNA-based therapy for the treatment of neurodegenerative diseases such as Alzheimer's, targeting the direct cause of the disease instead of its symptoms. The idea is to target the brain through different administration routes: intravenous administration, nose-to-brain delivery, and intracranial administration. So, taking all this in consideration, which is our goal? Our objective in this project is to develop a nanocarrier able to protect the RNA and facilitate the delivery of the therapeutic agent through the different biological barriers. One of the nanocarriers we are working on are RNA-loaded nanocapsules. This formulation consists of a cationic nanoemulsion composed of an inner oil core stabilized by a non-ionic surfactant and a cationic surfactant which provides the required positive charge for RNA binding. The RNA is electrostatically bound to the nanoemulsion and further coated with a polymeric layer. So, how are these RNA-loaded nanocapsules produced? The cationic nanoemulsion is produced using a nanoassembler. The organic phase is injected into the right inlet and the aqueous phase into the left inlet of the microfluidic cartridge. The corresponding parameters, such as the total flow rate ratio, and total volume, are sent in the software. The formulation is collected from the outlet stream, and the organic solvent is removed under vacuum. For the complexation of RNA, equal volumes of the nanoemulsion and the RNA are mixed under magnetic stirring, and then the system is coated with a polymeric solution. Regarding the properties of the nanocarrier, if we consider a nose-to-brain delivery, the formulation should have a size around 100 nanometers and a high RNA loading. In addition, the formulation should be stable along the time and in relevant medium such as cell culture medium and physiological medium. Let's see how the characterization of the formulation is carried out. The particle size and PBI are determined by dynamic light scattering using the synthesizer, and the same equipment is used for zeta potential measurements. RNA association efficiency is estimated by Aguirre electrophoresis. The nanocarrier is mixed with a glycerol and cybergold solution, and after loading it in the agar gel, it is run for 30 minutes to determine the free RNA. Up to now, we have developed protamine and polyarginine nanocapsules loaded with a model RNA that have around 100 nanometer size. The formulation is able to complex the RNA and it is stable for 2 weeks at 4 degrees. Our next objectives are to test the in vitro cytotoxicity and gene silencing efficiency of these nanocapsules loaded with a model siRNA. Future studies include the nose-to-brain administration of the formulation to Alzheimer's model mice. This is the end of the presentation, so I just want to thank you all for your attention.